the talk I'm going to go over the next few minutes is as follows. I did a study to ask the following questions, and I'm now going to present the data that has come from that. What is required to phase out fossil fuels? How big does the existing fossil fuel system, how big is it, and what does it actually do for us? What are the primary tasks of the green transition? And if wind and solar are the primary energy sources going forward, what will they need to function? And in particular, how big is the power buffer needed to manage intermittent supply? What is the quantity of metal needed to construct this system? Can recycling deliver this? And can mining deliver this? And if the green transition won't work, what might? So when we're talking about the global strategic decisions adopted by nations, like how we're going to phase out fossil fuels, for example, we're almost always talking about carbon emissions or associated climate change targets. We're not talking about the practicalities. For example, dwindling finite resources, the ones we're using now, and the ones that we're hoping to use going forward. The long-term physical logistics, there's no discussion about the number of physical units on the ground. The question is this: will this work for everyone? And will it work the way we hope? We're talking about the green transition, the plan to phase out fossil fuels, where wind and solar are now the primary energy systems, and all transport is now electric vehicles and hydrogen fuel cells. The pertinent question is, can we continue to resource this? So this is a map of the study. It's actually 3 maps. This is the first one. The questions asked were this: what were the physical tasks done by the industrial fossil fuel system globally in the year 2018? And for those tasks, what was the true scope of useful work? And if that useful work was to be done by non-fossil fuel units, how many units would there be? How many units are we talking about, and what work would they do? And if they were all assembled, what would be needed to resource them? And it turns out they need electricity to charge electric vehicles, batteries, and electricity to make hydrogen. Sum that electricity together, and using an energy mix proposed by the International Energy Agency for 2050, let's assume that happens, do the energy split and work out how many physical power stations are needed. The elephant in the room, and this was most surprising for me, was wind and solar are highly intermittent in nature. And to manage that intermittency, it needs a power buffer. What I didn't understand was the size of that buffer was much larger than conventional thinking allows for, and that all strategic planning so far hasn't really sort of thought through the need for that buffer and where they're going to get it from. At the moment, the buffer is fossil fuels, gas in particular. Right, so this is the power generated. In the column on the left is the power generated in 2018 across the year for the whole world. The white boxes are the fossil fuels systems that we want to phase out, oil, gas, and coal. The coloured boxes are the existing systems that we're to keep. The column on the right is the power grid that we need to actually bring in to maintain existing capability. So this is an extra 48,939 terawatt hours. The tasks are as follows: replace existing fossil fuel power generation, charge the electric vehicle fleet, the hydrogen production for the hydrogen economy, producing steel in a hydrogen atmosphere, production of ammonia, and the heating of buildings, mostly in the Northern Hemisphere. So the system will now expand to about 60,000 terawatt hours. It will more than double. So we are talking about bringing in a system that is more than double than our existing system, using electrical power generation systems that are simply not as effective and not as logistically flexible. And we still don't understand how to do that properly. So that's the old system, and that's the new proposed system. Here are the tasks, split up. So existing electricity demand is the black section down the bottom, and everything else is a new task. So when I started this work 7 or 8 years ago, everyone was focusing on electric vehicle batteries only, and they were looking at passenger cars only, which, as it turns out, passenger cars represent about a quarter of this yellow wedge. So all this time, we've been looking at only a fraction of what we need to do. And everything else. This is not a complete list. It is only the major actions. So here's a composite of what the Earth looks like from space without the clouds. So the global system, well, 1.4 billion vehicles. That's cars, trucks, buses, not including maritime shipping, rail, or aviation. This is just the transport fleet that we see, cars and buses and trucks. 1.4 billion vehicles traveled 16 trillion kilometers across the year 2018. So we need about 50,000 terawatt hours. And to do that, we need about 800,000 new non-fossil fuel power stations. And to put this in context, in 2018, the fleet was 46,423. So we are talking about a power station fleet more than 10 times what we have at the moment. This is what it looks like when we actually apply that energy split across what the IEA says. Wind and solar are now to take about 70% of the power grid. It's also, this is assuming that nuclear power is actually extrapolated all over the world. What was interesting is if you actually took this nuclear out, how much more wind and solar was actually needed? And the answer was a lot. The power storage buffer for this study is associated only with wind and solar, but in reality, the whole grid will need a power buffer. So how big should this buffer be? The US Department of Energy picked up my work in late 2021, and they contacted me and they said, look, your results are very different to what we think should happen. One of us is badly wrong. So we had a discussion about the data, what the assumptions were, and I suggested they go away and check a few things. And so they did. They then did an audit on their largest power grid that actually has renewable energy in it. So this is the PJM RTO system. It supplies 100 million people in the US. And they did this for a year, in the year 2022. And what they found is for 4 to 6 months of the year, wind and solar did indeed underperform. Not only were the capacity factors low, but they were low at the worst possible time. Like in winter, when we really want to spend more power on heating buildings, that's when solar really underperformed. In 2023, they did the same audit again, and they found the same pattern. So now we've got 24 months audit that is actually showing this basically, this basic idea, the buffer is actually much larger than we think. In practical terms, the information I collected from the Global Energy Observatory for the year 2018, what actually happened? So solar PV units turned out to be producing 11.4% of the time for the globe, for the global average, and wind was 24.9. So what this means is these systems, when we put them up, are vulnerable to the weather, and they'll be idle most of the time. There's not a lot we can do about that. The takeaway from all this is the power buffer is actually much larger than we think. So here is a case study in Spain where the sun's actually pretty good in summer, June, and in winter, November. It's not a standalone system, and it's balanced by gas and coal systems. But if it was a standalone system, it will be a 670 megawatt concentrated solar power system. The dark orange in this chart would be the power that would have to come from storage if this was to be balanced out to consistent power. What they found was for the month of November alone, that the power buffer would have to be approximately 16 days. 16 days, and they'd have to store it for something like 4 to 6 months, just for that 1 month. And remember, there are 4 to 6 months that are underperforming. So the takeaway from this is the buffer for that system where things work pretty well is 16 days. Right, so how big should this stationary buffer be? I'm using 4 references. 5 to 7 hours, or 6 hours, is what the conventional thinking actually believes. It's based on a study from Princeton University. We'll come to that in a moment. 6 hours. I've found several other references that scale all the way out to 12 weeks. Most of my calculations thus far have been on 28 days, which I selected as a conservative estimate, which when you look at solar radiance over across the seasons is actually quite conservative. Sensible answer to me is closer to 12 weeks. What's often discussed is, can hydrogen be used as a storage system? Well, let's look at that. So these are the capacities and the references used from 6 hours to 12 weeks. The electrical power that needs to be stored and sent back to the grid is here in terawatt hours, ranging from 25 terawatt hours out to about 8,000 or 9,000 terawatt hours. So if we were to actually make enough hydrogen to do this, that's the amount of electrical power that we would need to make the hydrogen to send the power back. And so we've got a ratio of about 4 times. That is, we need 4 times the electricity to make the hydrogen to send the power back as a power storage system. This actually is not good enough. And so hydrogen won't work as an energy system. Okay, here's the second map. So now that we have the amount of power that we need, how many physical units are needed to deliver the full system? How many cars? What kind? How many solar panels? What kind? How much steel, hydrogen, and ammonia needs to be produced annually? And what is the metal content for each wind turbine unit? What is the metal content of each solar panel in terms of kilograms per megawatt? And what battery capacity needs to be operating for this to work? Now, you might notice the battery capacity for the electric vehicle fleet is 65 terawatt hours. That is several orders of magnitude larger than any other study. All other studies I've seen have the battery capacity needed in gigawatt hours. And what they're talking about there is an estimate of what the market might be in 4 or 5 years' time, not a full replacement, which is supposed to be happening in 25 years' time. The stationary buffer ranges from 25 terawatt hours out to about 8,000 or 9,000. If we were to use the entire electric vehicle fleet as a battery buffer, it would only solve part of the problem. It wouldn't even, it'd be a rounding error at best. So what batteries are involved here? There are lots of batteries. There was a prediction of what batteries would dominate the market in 2050. All right, let's look at that. And what's metals in those batteries? Sum it all together, and then we've got the total quantity of metals required by metal. Okay, here's the third map. So now that we've got the quantity of metals, where do we get the metal from? Can recycling deliver it? Can the existing mining industry deliver it? Like, look at the mining production. Can the mining industry expand fast enough? As in, now we're looking at mineral reserves. If we were to bring mines on very, very quickly, what mineral reserves do we actually have that's associated with the feasibility study? What about long-range capacity? So if we looked at mineral resources, or what if we mined the sea floor? Would it help? Or, and this really is the answer, should we consider developing a fundamentally different strategic plan? So, here are the numbers. The big difference between these four outcomes is the size of the buffer from 6 hours out to 12 weeks. So everything's been summed together. All the electric vehicles, all the solar panels, their batteries, wind turbines, what have you, all summed together into this column here. Here is mining production in the year 2019. Now, I've used 2019 because it's the last year before the COVID disruption, supply chain disruptions, after which we're seeing some very strange artifacts in the data. So we're looking at the health and status of the mining industry. Let's pull copper out. We're look at just copper. Same numbers, but just copper. So here's our mining production globally. And here's the amount of copper that we actually need for the buffer, for the 4 buffers. Okay, if it's just 6 hours buffer, that's 12 years. We could probably do that. But when we get out to, say, 28 days, now we're looking at 250 years. Or the real number, which is, 12 weeks, now we're more than 700 years. The wrinkle is we've got to get it done in 25 years and 6 months. That is by 2050. this is probably not going to go as planned. All right, so here's the numbers. Remember, this is a log scale. I'm about to take this log scale away in a moment, but you really need to see the difference here. So the black is the mining industry production for 2019. The pink is the 6-hour buffer, and the blue, close to the real answer, is the 12-week buffer. Now remember, this is for the first generation of technology. We're actually going to come back to this, where in 10 to 15 years' time, your electric vehicle wears out, your wind turbines wear out, your solar panels wear out, then they have to be taken down and decommissioned, and we do it all again. So the existing industry cannot deliver. All right, let's look at the quantity of waste rock. If we're going to mine a lot of extra material, what will that look like? Well, between 1934 and 2012, the Australian copper mining industry mined a little, 2.8 billion tonnes. If we took the strip ratio associated with that in 2012, like what was the ore to waste ratio in Australia in 2012? And then we applied that to the amount of copper mining that is required to actually sort of hit these targets. And we're over 1,500 times that volume. This is such an enormous amount of mining. It would be environmentally disastrous, unprecedented, and impractical. All right, what about recycling? So what we've done here is, for the last 34 years, take all mining, everything that's been mined from 1990 to 2023. The globe mined 520 million tonnes. Okay, if all of that's on a waste dump somewhere now, because we've got like a cycle of around 10 years for most things. If we were to go to those waste dumps wherever they are, find all that, this is copper, find all that copper, recycle it, extract 100% of what was actually used, and then put it into manufacture, would that be enough? And the answer is no. So this is copper. When we get out to 12 weeks, we need 34.6 times that volume to actually manufacture the same number of units to maintain existing capability around us now. What this is saying is recycling cannot happen if it hasn't been mined yet. So there's copper, there's nickel, lithium. Lithium's a boutique metal that we've been mining on relatively small scales, but now we want to mine it like steel. That's why these numbers are so high. Cobalt, same basic pattern across all these minerals. There's graphite. Vanadium. The simple answer is this. What has not yet been mined cannot yet be recycled. So if we want to go this route and actually do this, this is a mining story, but can it happen? Right, so here is mineral reserves plus estimated resources and undersea resources. Now this is a log scale. This log scale will be taken and you will show a linear scale in the moment. This is all the metal that we know of in the system we call planet Earth. And that's in that hatched column on the left. Then we've got the pink, which is the 6-hour buffer, to the 12-week buffer. Let's look at this information in a linear space. This is harder to see, which is why I use the log scale to start with. As you can see, the amount of metal that we need is in the right-hand column here. The grey is reported reserves. That's actually something that we know is in the ground. There's some sort of economic feasibility study associated with it. The white is the resources. Areas of mineralized rock that we think are in the ground, but we don't know. The little black thing on the top, is the estimated volume of metals that we know of that are under the sea in resource form. Obviously, there's more down there, but this is all we know of at the moment. So this, at this point, is to point out that this is a crap plan. We really need to do something entirely different. This will not happen. It is not. We certainly won't happen in 25 years. All right, so let's look at sensitivity. The study that we put together, like how sensitive is it? What if solar became twice as effective in producing electricity? And the answer is, well, so when we see the sensitivity here, we've got this from 0, this is the baseline. The baseline's over here. The amount of copper we need, the amount of nickel we need, lithium, based on this calculation. But if something was to change in that calculation, how would this table change? And so if solar became twice as effective, the change is so small it's hard to actually see on the graph. And the same is for wind. What if wind became twice as productive as it is now? Or what would happen if the entire energy mix was all solar and wind in a 50-50 mix? All electrical power is now wind and solar. We've got a 30% increase over this table here of the amount of materials we need. Or what would happen if we were to increase the share of nuclear power? And if we take it out to 30% of the energy mix, then this table contracts by 30%. So what we've got is a difference between these two peaks here of 60% comes down to the choice of energy system we're actually looking at. What would happen if the battery market was dominated by LFP chemistries? There's now 80%. What would happen if solid state batteries dominated the market? And the last one, which was interesting, was if we would apply the Club of Rome degrowth model, but we also had to rebuild everything, what would that look like? Takeaway message here is this window is what happens when the nuclear power station fleet increases in terms of material consumption. The difference is about 8,000 tonnes of copper there and about 4,300 tonnes of copper there. Takeaway answer for this is mining, production, existing reserves and resources are not enough to manufacture for the first generation of renewable technology. I believe this is a black swan. It's a known black swan, but when it comes in, it will be such a surprise and it'll be so disrupting to many of the groups around me. We're coming to a close now. So let's say, what does this mean? The current plans for after oil are simply not good enough on multiple levels. Current thinking has seriously underestimated the task ahead. The green transition in its current form will not be feasible for all people and all nations. That's a hard thing to say, but that is what the data says. The technology to store power in large enough quantities does not yet exist. And until it does, wind and solar are not viable as large self-sufficient systems. They have their place, but they're not going to be the primary power source. They cannot be the primary power source for the next industrial era, and we need to think of something else. Hopes for a future technology breakthrough to somehow deliver more commodity resources do not seem to consider the nature of what we have to work with left and the nature of research and development of the mining industry over the last century. The current system has no concept of its dependency on minerals and does not consider long-term concepts like continuous growth in production against finite resources. Our society is energy blind and we are minerals blind. The solutions to this set of challenges are all around us now. We're required to get out of our own way. An attempt to expand the mining industry in such a step change would be environmentally disastrous. Required quantities of metals far exceed the known mineral reserves and resources. We do not have the time to explore for more, and quantities needed, even if they existed. Recycling cannot deliver the needed quantity of metals. There's simply not enough been mined historically to recycle. Inevitably, this leads to the conclusion that the renewable energy sectors and the EV technology systems are a stepping stone to something else rather than the final solution. It would behove us to give some thought about what that might be. Ecological reality and biophysical limitations will reassert themselves for the first time in centuries. So we should think about the way forward. Thank you. And that is my presentation. get it?